Hello, my name is Michael Yuan, and I'm a Docker captain, and I work at Gaia Network. Gaia Network actually has an office, engineering office in Singapore. So if you have time, you are more than welcome to visit us in our developer team. So I'm sorry I have to do this over video because I have a couple meetings in the US this week, so I can't be back in Singapore in time. But would love to meet you guys offline, when I'm there. So before we start, a lot of the content in this talk can be covered in my book. This is an ebook from Manning, so it's called Open Source Large Language Model on Your Own Computer. It covers running large language model and associated knowledge base, and things like fine tuning and things like that on your own computer, including in a Docker container. So before we start, let's have a quick overview of how people develop large language model application today. And in fact, if you look at most of the online tutorials and things like that, most people are using the large language model sidecar pattern. That is because when the large language model application first come on the landscape, it was mostly people using OpenAI APIs, and even today people are using Anthropic APIs or using APIs provided by AWS, right? All those large language models are hosted somewhere else, opaque to you with GPUs and all that specialized equipment. So your application would be mostly interacting with the large language model application through HTTP API. And in cloud native speak, that we call this pattern a sidecar, meaning the large language model itself is not integrated into application, but available as a service on the side, right? That is normally not a problem. However, I think over the past couple years, that's here is a very representative series of tweets from Elon Musk, right? When he took over Twitter, that he looked at all those essentially sidecar services presenting themselves as microservices, and so the architecture was overly complex if you look at it with the first principle thinking, and so you would think that's all those things they are fundamentally tightly integrated. They are fundamentally has to work together. One has dependency on another, but artificially broken into microservices. That's essentially sidecars, meaning independent services that can be accessed through HTTP, right? So I think the industry really have a movement that moving back from microservices since about 2 years ago. So if we look at large language model applications, the problem with microservices or those sidecar services is especially apparent because a lot of the large language model applications require really tight coupling between the application itself and the model that powers application. So for instance, the model evolves really fast, so it has to be strongly coupled with the runtime that runs it. So for example, if from the Llama to Meta's Llama 3.1 model to the Llama 3.2 model, it seems a very small increment, but the underlying runtime has to be at the exact right version. Otherwise, you would get the model would still run, but you would get the incorrect responses, which makes it really hard to debug, right? So there's tight coupling between the runtime and the model, and also there's between the model and the prompt. Some of the prompts that are going to work on OpenAI wouldn't work on Anthropic, wouldn't work on Meta. Something that works on the Llama 3.1 70 billion parameter would not work on, say, Qianwen 2.5 8 billion parameter. So you can't have the prompt managed in the application and have just the model themselves as sidecars. You have to couple the prompt with the model. Along the same line, the knowledge base, say if you have an application that's have ground knowledge somewhere else in a vector database, typical RAG application, you would have how the knowledge is being racked, how the knowledge is being chunked, are all dependent on the model that you're going to have to run. And different models also require different post-processing of responses. So meaning some of the model can follow instructions very closely, some of the model won't. Some of the model can generate tool calls, some of the model cannot, function calls. So there are all kinds of variations between models and applications that really requires tight coupling. So one of the arguments that's that I'd like to make is large language model applications are fundamentally tightly coupled. If you take one thing away from this talk, that'd be it, right? That'd be, yes, it's nice to develop applications using, say, LangChain or Llama Index plus OpenAI API, but fundamentally, you cannot really swap the OpenAI to another model with ease because there are lots of tight coupling that happens between your application and the model itself. Even if OpenAI made an upgrade, you would a lot of the prompts that you already have would break, right? So say when they moved from GPT 3.5 to GPT 4.0, a lot of the prompts that used to work wouldn't work anymore, right? So that really gives rise to the whole idea of why we want to run large language model in Docker. Not just the application that interact with large language model, but the large language model itself. We want to run it in Docker because we want to bundle or build the application with the large language model it depends on together, not as separate services. And when we have all those software that's work seamlessly together with the exact same version, with the exact right version, and with the exact right software components, that's a strong use case for Docker, right? Because then in that scenario, it's really difficult to get people to upgrade. That's because everything has to be matched together, and Docker is the ideal packaging mechanism to deliver this. Since this is a Docker event, so I guess this should be obvious to us. So what's inside our Docker container? So before I go to the demos and all those details, let's go discuss a little about the selection of technologies, right? So when we say run application together with large language model, I asked this question many times during my conference talks and user group talks, and most people would raise their hand to say just use Python and PyTorch, right? Because the client-side application or the middleware application is typically written in Python, Longchain, DeFi, or Streamlit, things like that. And then you can just run the model using PyTorch on the same machine, or that's you bet, right? That's you have an application that has both the application and the large language model it depends on. However, the problem with Python is that it's extremely bloated at this moment. So if you look at the screenshot at the top right, the PyTorch Docker image is 8 gigabytes. Okay, that's larger than large language model itself. In many cases, and it has huge dependency. Because of the bloat, it has huge dependency and complexities. And because of these complexities, opens up for things like supply chain attack, and also incompatible versions. If you have any application that's requires something that is slightly outside of the mainstream Python packages, it's likely to cause conflicts and things like that. So people spend a lot of time managing those complexities that has been crept into the Python ecosystem. And the Python inherently is also a very slow language. And so it's up to 4 orders, 10,000 times slower. There's a lot of papers and benchmarks that demonstrate that, right? So even if in the large language model application scenario where the heavy compute happens on the C++ that underneath the Python library, like Torch underneath PyTorch, right? The slowness of Python in critical areas like tokenization can still be felt, and it can really slow down your application in use cases like real-time applications, so voice to voice, and it's image recognition and things like that. So Python is really not, in my opinion, it's a great choice for experimenting with those models, but it's not really a good choice for embedding model into your application. So here are some, famous people talking about this problem, right? So Greg Brockman is a founding member and CTO of OpenAI, and we all know who Elon Musk is, right? So it's I think it's quite well recognized that Python is not ideal framework for high performance inference. Well, so if not Python, the second choice most people have is a package software like Llama, right? So you just download Llama, sort of like Docker, and you load Llama, pull Llama around, right? That is great. I use that as well for experimenting with the models, but it also has some really severe drawbacks. So for instance, Llama only, by its name, it supports the Llama architecture, right? It mostly supports large language model and sometimes, the vision language models. But the agent application in your, when you build an agent application that embed, different models, you often need to have multimodal capabilities, meaning you need to embed a model that turns voice into text, and then use the large language model to process the text, and then the text back to voice, so that you build a sort of phone call experience, right? So we're gonna have an example really soon. So there's lots of use case, lots of models that Llama can't run, but we need in our application. So it makes it difficult. You need additional tools other than that in order to embed those models into your application. Another problem with that is the operational weight, because it is designed to be easy to operate. But because of that, Llama essentially is a Go application built on top of llama.cpp. It incorporates, it has multiple platform-specific binaries packaged into the same application, so it detects which platform you are running and then route it to the correct binary to execute it, which make it easier for, say, first-time users. But it's unnecessary bloat, if you like Python, right? If you are going to use it in a, say, a lightweight inference structure. And also it requires a super user daemon in order to monitor its status. It depends on external internet-based model hub. So all those things add weight to its operation and to its deployment, right? So that's yes. By the way, I would say that you can definitely use Llama, and I would encourage you to, because I use it myself. But I just felt that it's not lightweight enough to do applications that it needs embedded large language model, right? So now we talk about Llama, and we talk about underneath Llama, it's really a C++ framework called llama.cpp. Can we use that directly? Because then you have llama.cpp, you can also have whisper.cpp, flux.cpp, and all those C++ based frameworks that do give you a selection of different models. Just to combine those C++ based framework together and write your own framework on top of it, right? But that's exactly the point. That's make it difficult, right? Because those are all C++ APIs. You have to write your own wrappers, and it's an arcane language. And then if you do it in C++, it creates safety issues, memory leaks, and all things that are associated with that language, right? So so that's not ideal as well. So that's brings us to our approach to running large language model in Docker, right? So we have a Linux Foundation CNCF project called LlamaEdge, and the LlamaEdge is a WebAssembly runtime. So it allows applications developed in multiple different languages to be compiled to WebAssembly. And on top of that, we expanded that specification to make WebAssembly a GPU abstraction as well. So meaning the same WebAssembly binary can be adapted to the different underlying GPUs. So you just write applications according to a spec, and then compile that application. And then the binary application that is in WebAssembly or in Wasm would be able to know which underlying GPU it calls, right? So if it runs on the Mac, it's going to call the M1, M2, M3, M4 GPU. If it runs on a NVIDIA device, it's going to know it's going to call the CUDA GPU. If it runs on a Huawei device, it's going to know it's going to call the CAN GPU driver. So so it provides abstraction, allows different GPU applications to be cross-platform, and that abstraction is called the LlamaEdge, right? So the LlamaEdge is Rust-based framework on top of WasmEdge that allows people to build modern applications that take full advantage of large language model without worrying about GPU capabilities. So so here are some advantages that I listed here. So it's essentially cross GPU platform compatible, and it's model agnostic, meaning it supports all the models that are out there. That's anything you name it that is going to support it, because it supports the Torch framework, which is really the runtime underneath PyTorch without all the Python garbage, without all the Python baggage, right? So this is the runtime that we want in our Docker container. And to go one step further, we not only have the large language model and its runtime, we also have associated services, for instance, the vector database, the prompt management tools, and the API server that allows application developers to access our service through OpenAI compatible API, and networking supports through HTTPS, and even building access and payment gateways. So all those things combined together in a single Docker image is called Llama Network. That's where where I work, and where the office is in Singapore, right? So if you're interested in the Llama Network, you can scan that barcode, you go to our GitHub repository, and you will get started have a large language model running on your own laptop before you leave this talk today. Okay, I promise you that's only takes like 10 minutes, right? So if you're interested, just do that right now. Okay. So now we have the basic introduction of why we need a Docker container. We need to have large language model together with the application to have them tightly coupled instead of having the large language model as separate service. Best way to deliver this coupled experience, tightly coupled experience, is package everything together, including the vector database and everything else, into the same Docker image, right? So let's see how it works. And if you go to the Docker Hub, because we are here at the Docker event, so I don't think I need to tell you guys to install Docker, something like that. I assume you all have it, right? So just run this Docker command, pull a pre-made container onto your own device and start using it. So once you run this device, once you run this container, it maps the 8080 port inside the container into the 8080 port onto your host. Then you can load the localhost 8080 from your browser. And from that, you will see something like this. You will see a chat interface where you can interact with a large language model that's running inside the container, right? So in this particular case, we have a large language model together with a knowledge base that's full of the Rust knowledge. So let's take a step back. So most of the one of the most interesting application of large language model is to be a coding assistant, help you write code, right? But most large language model out there is trained on, say, Python or JavaScript code. They see very little Rust code in their training. So in order to fix that, we build a fully integrated application that has not only the large language model, but also a knowledge base from the Rust Foundation, taking advantage of all the open source Rust knowledge that's out there that's managed by the foundation, essentially those books, tutorials, and example applications, and put that into the knowledge base to ground the large language model. So as a result, we can have an API service and also as a chatbot, as we see here, to help user learn and program in Rust, right? So if I say convert a string to an integer, I'm not saying to do it in Python or to do it in JavaScript. If you ask this on ChatGPT, it's gonna give you a Python answer, or it give you a JavaScript answer. But here it already knew it's gonna program in Rust, and it knows where to find relevant information in the Rust documentation and examples, and then come back, I think, with a really good answer. And there's even a little play button here. If I, as you can see here, if I click on that, it actually gives the result of running this main function, right? It also tells you, that you need to handle, error properly in the proper way that's required by Rust. So it's I believe it's a really good answer. And the thing that I want to emphasize is that it's a really small model. It's a Qianwen 500 million parameter model, making it suitable running on GPU, on any CPUs, even slow CPUs. So that's that's why we made it available here, right? So you don't really need a GPU device or a Mac device in order to run this model, because it's really small. Even on a very small old CPU, it can get 50 tokens per second. That's 50 tokens per second is 5 times or 10 times than how I can speak, right? I speak about 5 tokens per second, right? So so it's I hope this is a demonstration of a really powerful integrated large language application with integrated large language model and the knowledge base that is specifically tailored to this large language model. So to take a step further, because we have seen that's how the chatbot interface, but a few people actually use the chatbot. That's I take back. A lot of people do because of ChatGPT, but it's not really a natural an interaction mode for programmers, right? So one of the most interesting aspect of it is that once we have this application running inside Docker, it not only provide a human interface through the chatbot, it also provides API that allows it to integrate with the leading IDEs. So in this example, we'll show that this Rust agent integrated into Cursor, right? So Cursor AI is one of the most popular coding IDEs out there, and there's a a three-step instruction, in terms of how to integrate this model running inside Docker with into Cursor. So you can go to the website and see it. And once you have done that, I have a quick demo in terms of how that works. Without further ado, let's get started. First, we'll add our self-hosted Q1 coder model to Cursor settings. We make sure that all other models are turned off. Our project is a database-driven web application built in Rust. We'll focus on two files. The SQL file contains a database schema. We can see 3 tables, including a messages table. The Rust source code file is a web application based on a popular web framework. We use structs to model database tables in the Rust code. Let's open the AI context. Notice the model we use is our own self-hosted model on Llama Network called Q1 Coder. I tag both the SQL file and the Rust file in the context and ask the AI to create a struct for the messages table in the SQL database. But many Rust APIs have structs named message. To avoid this conflict, let's change the name to log message. Now it looks good. Can we apply the change to the file in the editor? Nope, I have not paid. So I guess the code merging is done with their special model. But the code completion tool in the editor is aware of the chat session to the left, so it is able to auto-complete the generated code. Not bad. Next, I ask it to write a HTTP request handler for a new API endpoint. It retrieves log message from the database and returns as a JSON string. Cool. The handler and HTTP route are both here. It is important to note that Cursor is able to mimic similar functions in my code to create new functions. For example, it knows the web framework I'm using. Finally, let's go to our self-hosted API server and look at the actual prompts. We open the LlamaEdge log file. The system prompt is written by Cursor. It gives overall instructions. It also has relevant Rust knowledge we supplemented to the node. The user message includes files tagged in the chat context and the user question. With the prompt and the context, the AI is now able to generate Rust code. That's really quite straightforward. Okay, so now we have seen a complete demo of a fully integrated application with large language model and a knowledge base, and how it become a coding assistant in the IDE environment, right? So next, I want to give you another more complex demo. This demo is really a project the community built called videolangua.com, right? What it does is that it's a fully integrated application, but not with, but in addition to the knowledge base, it also have multiple models and multiple agents. So the effect is that when you go to this website, you can upload a video file, and it would translate that video file into another language. For instance, English to Chinese, English to Japanese. That's so it could add the soundtrack of Chinese to the original English, or add closed caption. Right. So the way it works is that the application has a complex workflow that coordinate multiple embedded agents. They are all combined into the same application, right? So one of the agent is Whisper, which is voice to text. So it detects the voice from the original video clip and turn that into text, right? English text. And then we use a large language model. Here we use Qianwen 70B, and with the proper prompt to translate that into Chinese. But sometimes it translates wrong. Sometimes it answers question instead of providing the translation. So we have a second model, which is the Llama 3B, Llama 3.1 8B model, to check the translation quality and give feedback to the Qianwen model. So those two models goes back and forth, and to provide the Chinese transcript of the video with timestamps. And then we have another model that called the TTS, right? That's to do the text to speech. So it takes the translated Chinese text into Chinese speech or into closed caption, and then put it back onto the original video. So this whole application can be packaged together because all those models needs to work together. It's really difficult because of the amount of prompting and the amount of customization involved. And so for instance, there are certain ways that the Qianwen 2.5 model going to follow instructions. So there's post processing to figure out whether it did provide the translation or not, or whether it has obvious problems. For instance, it's a large amount of English texts were not translated sometimes, right? So there's lots of workflow optimizations that are very specific to the model that we use, and all those, including the models, runtime, and everything, are packaged into a Docker container, and so that all those applications can all run together. That's what we say, the tight coupling between the application and the models, right? So I hope this example really showcases that. I don't have the time to do a demo here, but because this website is public, any of you can just upload a short video clip and see how it works, right? That's all good. But the title of the talk is really portable cross-platform Docker applications, right? So the way that we package Docker container is not really cross-platform yet because, depending on the underlying GPU platform, it's gonna have different APIs inside the Docker container, and the LlamaEdge runtime the LlamaEdge runtime would have to adapt to that. So you need different versions of LlamaEdge in order to match the underlying GPU driver. So the application itself is cross-platform. You just write the application in Rust and compile it once, and then run on all GPU platforms. But the runtime underneath that runs the WASM application is not cross-platform, right? It has to translate the WASM instruction into GPU instructions. And because of that, if you go to our GitHub, if you go to our Docker Hub, you would see CUDA 11, CUDA 12 versions of those Docker images. So that's not really optimal. So so we do more? Especially with there are so many GPU platforms out there. There's really a need to be more abstract and to be more portable, right? So that's one of the things that we worked closely, with the Docker team since almost 2 years ago, is to make WASM another container format in the Docker ecosystem, not just the Linux container, but the WASM container, right? So with the WASM container, we can move all this driver management and device management into the Docker host. So the container and the guest application in the container would be completely portable. They would not have any GPU knowledge or any GPU dependencies, right? So I would have an application that compiled WASM, and it would automatically know whether it's going to run on the Mac GPU or on the CUDA GPU or AMD GPU, depending on what capabilities the Docker host provide to it, right? So that's what we call the Docker plus WASM approach. And if you're interested, there's documentation, and you can just go search for Docker plus WASM, and WASMEdge is one of the first WASM runtime. It's the only large language model capable WASM runtime that integrated into Docker Desktop today. So it has very clear benefits. It's portable. It's supported in all the Docker tools. So over the last 2 years, we have it running inside Docker Desktop, run WASI, Podman, crun, OpenShift, Kubernetes, and all that. So the single binary file can be portable across all the different cloud native environments, regardless what's the underlying hardware and software platform. Of course, the disadvantage of that is the application has to be compiled to WASM, so it's not an operating system environment. So it's pretty much can only run the large language model. So for instance, it's going to be difficult to run a vector database in the same container that's not yet compiled to WASM, right? But there's the solution for that really is to use things like Kubernetes or Docker Compose, right? You have different components that can be tied together in a single deployment. So that's pretty much all I want to cover in this talk. And there's really one more thing is something that's over the horizon is the Docker support for WebGPU, meaning that's as I described, one of the big problem is that different GPU platforms gonna have different APIs inside the Docker container. So so in that way, you are coupling the host with the guest, right? So the web GPU in a way that's the LlamaEdge or the WasmEdge approach separates that by having a high level inference API that's independent of the underlying GPU platform in a guest environment or in a container environment. And another way to do it, which goes into much lower level APIs, is called the WebGPU. So the Docker team has been actively working on providing WebGPU APIs and support in the container environment. And we would love to hear your feedback in terms of how you like it, whether you want to use it. And there are some examples that's technology preview that we have demonstrated how WebGPU works with WasmEdge in a Wasm container environment. So anyway, yeah, that's I know we covered a lot of ground, and so if there's one thing you want to take away, is a large language model really needs tight coupling between the application and the model, and the best way to insulate the model to package the application with the embedded model is using Docker, and the best runtime to use that within Docker, the most lightweight, portable, and model agnostic runtime for this purpose is WasmEdge and LlamaEdge. Thank you very much.